In this presentation, I'll be explaining maximum power point tracking, MPPT, to extract maximum power from the solar power, PV power system or PV system. Okay, now let us see what is maximum power point tracking. Now let us see the PV panel characteristics, the maximum power point. PV panel characteristics, there are two characteristics. One we call it as current voltage characteristics or IV characteristics. Second one we call it as power voltage characteristics, PV characteristics. In IV characteristics, y-axis is the current and x-axis is the voltage. Current voltage characteristics. And for different irradiance, that is, for example, here 1000 watts per meter square. And in that one, this is the current versus voltage characteristics, or this is what we call it as short circuit current, and this is called open circuit voltage. Therefore, this is the voltage axis and this is the current axis, and this is the IV characteristics corresponding to 1000 watts per meter square of irradiance. Now, if you calculate the instantaneous power by multiplying the instantaneous voltage and the current, then we will be getting the power as such. Therefore, if you plot the power versus voltage, therefore this is the axis voltage and this is axis equal to power, then it is called PV characteristics, or here corresponding to 1000 watts per meter square, this is the PV characteristics corresponding to that. Therefore, this is the maximum power, or this is corresponding to 1000 watts per meter square of irradiance. Now, as the irradiance changes, for example, it is 800 watts per meter square, short circuit current is reducing here from 1000 corresponding to 1000. This is the short circuit current. Now the short circuit current has been reduced, and open circuit voltage is also slightly reducing. Therefore, the reduction in short circuit current is more than reduction in short circuit current. Sorry, open circuit voltage. Therefore, this is the IV characteristics corresponding to a irradiance of 800 watts per meter square. And you can plot corresponding PV characteristics below that one. Therefore, this is corresponding to the PV characteristics corresponding to 800 watts per meter square of irradiance. Like that one, for different irradiance, you can plot what is the current versus voltage characteristics. And as irradiance reduces, you can see that one, this IV characteristics going down as this one. Therefore, this is a reduction in the short circuit current is reducing. Similarly, the open circuit voltage is also reducing. Now, you can, if you see that one, this is the PV characteristics for different irradiance. As irradiance reduces from 1000 watts per meter square to 200 watts meter square, you can see that one, the maximum power is getting reduced that one. Therefore, for a given irradiance, the panel have a unique operating point called maximum power point. Therefore, for 1000 watts per meter square, this is the maximum power point. So, for example, this is for 800 watts per meter square, this is the maximum power point. Then where the maximum power point, where the output power reaches it to a maximum value. Therefore, the maximum power point tracking is used to operate the panel at MP maximum power point irrespective of the load. Whatever be the load, irrespective of the load, it has to operate at the maximum power point. That is done by maximum power point tracking. Continuing the IV and PV characteristic curve of a solar panel system as such, and maximum power point, that is, this is the IV characteristics, this is the short circuit current, and this is called open circuit voltage. And if you multiply the instantaneous voltages and current, you can get what is the power. Therefore, this is the PV characteristics, and this is the maximum power, and corresponding to the maximum power, the corresponding voltage, we call it as VMPP. That is, VMPP is the voltage corresponding to maximum power. Similarly, if you see this one, that is this point, this is the maximum voltage corresponding, the voltage corresponding to maximum power, and this is the current corresponding to the maximum power, or this is called, so IMPP, and this is called the VMPP. And the product of VMPP and IMPP, or VMPP into IMPP, will give what is the maximum power. It is equal to PMPP, or PMPP equal to VMPP into IMPP. And this is the maximum power, and this is the voltage corresponding to the maximum power, and this is the current corresponding to the maximum power, and the resistance corresponding to this point, that is corresponding to the maximum power, is this one, and corresponding to that point here, this is the point that in the IV characteristics. And if you draw a line passing through that one, the resistance corresponding to that one, that we call it as RMPP, resistance corresponding to the VMPP and IMPP, or nothing but VMPP divided by RMPP is called VMPP divided by IMPP is called RMPP, or resistance corresponding to the maximum power. This is the resistance of the panel corresponding to the maximum power is this one RMPP, which is nothing but VMPP divided by IMPP. Therefore, the point at which the product V and I is maximum in VI characteristics of the solar cell is defined as maximum power point, or that is called the maximum power point as such. And maximum power point is a unique, and it is located at the knee of the PV characteristics. Therefore, this is the PV character here, this point corresponding to this point, the product of IMPP and VMPP, that is called the PMPP, maximum power point. Therefore, the MPPTs are used to track the peak power by operating the PV panel at the peak voltage. If you operate the PV panel at this peak voltage VMPP, then you can extract the maximum power from the solar panel. Therefore, this is the resistance corresponding to that maximum power. The solar panel resistance corresponds to the maximum power equal to RMPP, which is equal to VMPP divided by IMPP. Now let us see the variation of this resistance RMPP for different irradiance. For example, for 1000 watts per meter square, this is the IV characteristics, and to the knee point from the origin, a straight line is drawn, or this is the resistance correspond at this point, and that resistance is a RMPP corresponding to 1000 watts per meter square. Similarly, if irradiance is reducing to 800 watts per meter square, again to this knee point, you draw a straight line from the origin, or the resistance represented by this one, or that slope, this one, that is equal to RMPP corresponding to the 800 watts per meter square. Therefore, as irradiance reduces, we can see that one resistance is increasing. That is, we can see that resistance increases as irradiance reduces. Therefore, here the RMPP is the resistance corresponding to the maximum power point, and here PMPP, as is already done, VMPP into IMPP, RMPP equal to VMPP, voltage corresponding to maximum power divided by current corresponding to the maximum power, or VMPP divided by IMPP, where the RMPP varies according to the irradiance. Therefore, as irradiance changes, RMPP will be changing, or you can, in this one, it is clear that as irradiance is reducing, the RMPP is increasing. Therefore, the maximum power point track has to adjust the duty ratio. We'll see that one of the converter, such as to make the resistance same as the RMPP. Then maximum power will be transferring from the solar panel into the load. Now let us see the load resistance required for maximum power transfer. Load resistance required for the maximum power transfer. Now this is the solar panel, and the output is connected to a load as such here. And the maximum power of the load, the maximum power can be transferred into the load if the resistance of the solar panel is same as the load resistance. That is, maximum power transfer theorem states. Therefore, here, for example, the IV characteristics of the solar panel for a certain radiation is this one, and the resistance corresponding to this one is the slope of this one. Therefore, if again you are increasing the resistance so as to pass through the knee point, this corresponding to the resistance of maximum power point, that's RMPP. This corresponding to RMPP, or that is passing through the knee here, and this is RMPP, which is the maximum power point resistance of the solar panel. Now, if you make the load resistance same as RMPP, the maximum power can be transferred from the solar panels into the load. For the same as we have seen this one, this is the PV characteristics of the solar panel. This is the IV characteristics. This is the maximum power point. This is the voltage corresponding to the maximum power point, VMPP. And this is the current corresponding to IMPP. VMPP into IMPP equal to PMPP. And the ratio of VMPP to IMPP. VMPP divided by IMPP, or that is nothing but this slope of this line, that represents the RMPP. Resistance of the solar panel corresponding to the maximum power point is given by RMPP, which is equal to VMPP divided by IMPP. Therefore, the solar panel can deliver maximum power into the load if and only if the output load, that is this load resistance, is same as RMPP. Then maximum power can be transferred into the load. Continuing the load resistance requirement for maximum power transfer, here as we have seen, this is the IV characteristics for certain irradiance. Therefore, if the line, if this is passing through a point through this, that is the PB1 corresponding to resistance R1, this is the point at which it passes. And if you plot the same thing in PV curve characteristics corresponding to that B1 is this one, or this much power can be extracted if you ask for the resistance this one. Now again, if resistance is increased to a point passing through the knee of this one, that is the point passing through B2, that the corresponding resistance equal to R2. If you plot the same thing in PV characteristics, or it is passing through this one, or it is passing through this point, or it is passing through the maximum power point. Therefore, if the resistance passing through the knee of this one, that is going through the maximum power point, that is B2, same as B2 here, B2 comes here. Now again, if you are increasing the resistance more than this one R3, which R2, that is R3 is more than R2, that is be passing through a point at B3. The corresponding point in PV curve is this one. Therefore again the power extracted is less. Therefore the maximum power can be extracted if the load resistance is, or if you are making the load resistance same as RMPP. Therefore here R1, R2 is more than R1, again R3 is more than R2, or if you select a value of R2 as the same as the load resistance, that is nothing but RMPP, then maximum power can be transferred from the solar panel into the load. That is, it can extract the maximum power, it can make to work the operating point at B2. Therefore again, PMPP equal to VMPP into IMPP, and RMPP equal to VMPP divided by IMPP. Now let us see how this maximum power point tracking can be implemented. How can it be implemented? In that one, we have to use a converter. In between the load resistance and the PV panel, we are using a converter. DC to DC converter is used. The DC to DC converter can be a non-isolated, like boost converter, buck converter, or buck boost converter, or it can be isolated one, flyback converter, push-pull converter, forward converter, half bridge converter, or full bridge converter. Any type of converter can be used. DC to DC converter can be used between the solar panel and the load. Therefore, as already we have seen, this is the IV characteristics of the solar panel, and the corresponding PV characteristics is one. If you want to extract the maximum power from the solar panel into the load, what we have to make the resistance of the load, or the resistance looking at this point, because if the load resistance you cannot adjust as such. Now if you control the duty ratio of the converter, DC to DC converter, if you control the duty ratio of that one, the resistance that is reflected at this point can be varied. We see like that one. If you make that resistance reflected, the load resistance reflected at this point same as the RMPP, that is this resistance, then maximum power can be transferred from the solar panel into the load. Therefore, basically you are controlling the duty ratio of the DC to DC converter so as to make the load resistance reflected at the input point same as the RMPP resistance corresponding to this, that is this line. We are making that one. That is done by controlling the duty ratio of the DC to DC converter. Therefore, the duty ratio D is adjusted to modify the equivalent load resistance seen by the source. That is, what is the resistance seen at this point, that is made equal to RMPP. That is done by controlling the duty ratio of the DC to DC converter, where here RMPP means that resistance corresponding to the maximum power point, that is this resistance corresponding to this one, VMPP divided by IMPP. Therefore, that is the principle of maximum power point tracking implementation using DC to DC converters. Continuing the maximum power point tracking, as we have already seen, we can use either a buck converter, or you can use a boost converter, or a buck boost converter can be used. Any type of converters can be used. And here what I am going to explain is a buck boost converter. We are using a buck boost converter, that is between the solar panel and the load, we are using a buck boost converter. And if it is a buck converter, as you see that one, the input resistance at the source side at the, that is equal to output resistance divided by D square. And if it is a boost converter, input resistance, that is resistance seen at this point, is equal to what is the output resistance divided into 1 minus d whole square. For a buck boost converter that we are going to discuss, which is equal to the resistance seen at this point, which is equal to output resistance into 1 minus d whole square divided by d square. This is for a buck boost converter that we are going to explain that one. And to derive this equation, that is what is the relation between the resistance seen at the source side and the output resistance. In order to derive that relation, this relation, we'll first consider the buck boost converter voltage ratio equation. D0 divided by VD, output voltage divided by the input voltage equation for a buck boost converter is given by D by 1 minus D, and the relation for the output current divided by the input current, I0 divided by ID equal to 1 minus D divided by D. From these two equations, you can get what is V0 equal to dVd divided by 1 minus D, and I0 equal to 1 minus D divided by D. Therefore, once you get V0 and I0, you can calculate what is R out. R out equal to V0 divided by I0. Therefore, this one divided by this one, or we'll be getting it is equal from these two equations, dividing this one with this one, you will be getting D squared Vd divided by Id into 1 minus D whole square. Or Vd by Id, that is the voltage at this point is the Vd, and the corresponding current equal to Id. Vd by Id, that is the resistance seen at this point. Vd by Id, that is equal to R in, or the resistance at the seen at the source side, or this resistance at this point, that is equal to R in into D square divided by 1 minus D whole square. Or you can say that R in equal to the resistance at this point equal to output resistance into 1 minus D whole square divided by D square. Therefore, that is this relation, Rn equal to R out into 1 minus D whole square divided by D square. Therefore, by controlling the duty ratio here, you can control the resistance of that is seen at this point, and we are making this resistance same as the RMPP, that is resistance corresponding to the maximum power point. Therefore, where D is the duty ratio, which is equal to on period divided by total time period. Duty ratio of a switch is called duty ratio of this switch, we call it as on period divided by the total time period. That is called the duty ratio. By adjusting the duty ratio, we can make R in same as the RMPP. Therefore, this is the diagram corresponding to the buck boost converter and the solar panel. This is the buck boost converter. Switch is the, inductor is the, diode is the, and this is the load. This is a buck boost converter, and this is control using a MPPT control algorithm is there. We'll see later. In order to that sense that one, we have to sense what is the instantaneous voltage, solar panel voltage and solar panel current is to be taken. Therefore, based on that one, that will be fixing the duty ratio of this switch. Continuing the MPPT control using a buck boost converter. This is the buck boost converter. This circuit is a buck boost converter, and the solar panel power is given to the buck boost converter, and we are controlling the duty ratio of this switch, that is by using a MPPT controller, in which we are controlling the duty ratio D such that this one 1 minus D whole square into D into R out, that should be same as that is R in, which is same as RMPP, that is resistance corresponding to the peak power, that is VMPP divided by IMPP, that is RMPP. Corresponding to that one, we will be adjusting the duty ratio and make this resistance R in same as RMPP. That is done in the MPPT controller. Therefore, RMPP is the resistance corresponding to the maximum power, and R out is the output resistance. R in is the resistance reflected at the input side of the converter, or the resistance seen by the panel. For a buck boost converter, as we already derived, buck boost converter, R in equal to R out, this resistance into 1 minus D whole square divided by D square. Will be controlling the duty ratio such that this R in resistance is same as RMPP. Then it will be working, or the maximum power can be transferred from the solar panel into the load. Continuing the MPPT control using a buck boost converter. This has already seen PV panel. Buck boost converter is the, load is the, this MPPT controller is the, by controlling the duty ratio of the switch. Duty ratio is equal to on period divided by the total time period. But T on divided by T total time period is equal to duty ratio. By controlling the duty ratio, you can make the resistance of this seen at this point same as RMPP, as VMPP divided by IMPP. As we have seen here, this is the resistance corresponding to the RMPP, And if you are increasing the resistance, except that will be operating another point, which will be after the maximum power point. Therefore, we want to work at the maximum power point means that we have to make this resistance same as the RMPP. Therefore, adjusting the duty ratio of the converter such that Rn equal to R out into here, not this equation, Rn equal to R out, this not this one. Say this is for a boost converter. This is buck boost converter. This is the equation. Rn equal to R out into 1 minus d whole square divided by d square, and we are making that one is equal to RMPP. Or here, as an example here, R out equal to 20 ohms. This is equal to 20 ohms, and RMPP is equal to, that is 13 ohms. Therefore, now if you adjust the duty ratio of the switch so as to make as D equal to 0.554, if you make adjust to that point, then if you substitute that one, we can get Rn equal to the resistance at this point, seen at this point. That resistance is equal to, again, if you substitute that one, that is equal to 13 ohm, which is same as RMPP. Therefore, the resistance seen at this point is made same as RMPP. Then maximum power will be transferred from the solar panel into the load. That is called maximum power point tracking. In this buck boost converter, here you are adjusting the duty ratio and making the load resistance equal to same as the RMPP. This represents the block diagram of a MPPT controller, and in that one, as we have already seen, PV array is the PV panel is the, and there's a converter, DC to DC converter is the buck boost converter, as we already seen, or buck boost converter also it can operate, buck boost converter, and that is given to the load here. And to control the duty ratio of this switch of this converter, we have to, there's a MPPT controller is the that monitors the instantaneous voltage, PV voltage, as well as instantaneous PV current. IPV and VPVs are monitored, and based on certain algorithms, that's maximum power point algorithms are there. Based on that one, it can calculate the required duty ratio, and corresponding power can be, maximum power can be delivered from the PV panel into the load. That is in the maximum power point tracking. Now let us see the maximum power point tracking control algorithm. Widely used one is called perturbance and observance, P&O algorithm. P&O techniques is the widely using that one. For the perturbance and observance, P&O algorithm is widely using in MPPT control for photovoltaic systems. Therefore, here the algorithm works by, that is actually we are doing a disturbance, a perturbance, slightly changing the operating point of PV array done by changing the duty ratio, then observe the effect on the output power. As we have seen that one, this is the PV characteristics. We see that one. This is the PV characteristics. Now here, assume that this is operating point is somewhere here. Therefore, the maximum power point is here. Now what we are doing is that we are giving a disturbance to this operating point. Then when giving a disturbance, there will be a change in power, delta P, as well as there is a change in voltage. Then we will see that the ratio delta P and divide by delta V. If that is positive, meaning that the point is somewhere to the left side of this one, then you have to again increase the voltage so as to reach to the maximum power point. Therefore, we are basically watching what is the delta P by delta V. For if it is operating at the right side of this one, you can see that one, if it is shifted here, delta P by delta V will be negative. Therefore, then you have to shift or reduce the voltage and bring the operating point to the maximum power point. Therefore, here the algorithm is working. Let's see first one, initialize the variables and setting. That is, what we have to do is that instantaneous voltage, solar panel voltage and currents are monitored. First thing, you are monitoring the instantaneous voltage and current of the solar panel, and then we'll be calculating what is the instantaneous power. Instantaneous power is given by instantaneous voltage into instantaneous current. Therefore, this is the instantaneous power of the solar panel, or that can be calculated, and then that voltage perturbation is done. We are slightly changing the operating point, or we are doing a certain perturbation in the voltage, or delta V change in voltage is done. Measure the new voltages after perturbation. The voltage has been changed from Vn to Vn plus 1, and the current has been changed from current I to In plus 1. Then take the product of that one, Vn plus 1 and In plus 1. Then we'll be computing the new power, Pn plus 1. So previously it was Pn. Now it is changing to Pn plus 1. Then we'll be changing what is the change in power. That is delta Pn is, or delta P is calculated. Pn plus 1 minus Pn. That will be calculating what is the delta Pn, or the change in power. Therefore, after calculating Pn and Pn plus 1, next what we'll be doing is that Pn plus 1, Pn is compared. Whether if Pn plus 1, that is if the power calculated at certain instant is more than the previous instant, that means that it is in this region. The operating point is in this region. Therefore, if Pn plus 1 is more than Pn, perturbation has moved the operating point closer to maximum power point. That is, perturbation has moved the operating point closer to the maximum power point. And continue the perturbation in the same direction, then we'll be doing the perturbation, that is doing the voltage change, that is the same direction, increase the operating voltage by delta V, update the voltage at Vn equal to Vn plus 1 and Pn equal to Pn plus 1, and we'll be moving the operating points slightly above, and that will be finally reaching to the maximum power point if the operating point is left side of that one. That is, if Pn plus 1 is more than Pn, move the operating point towards the maximum power point. Continuing the perturbance and observance Piano technique. Here, if the Pn plus 1 magnitude, or that is equal to less than, magnitude is less than Pn, that means that operating point is after the maximum power point. Perturbation has moved operating point away from the MPP, and then what we have to, in order to reach the maximum point, we have to reverse the direction. That is, you have to reduce the voltage, reverse the perturbation, or you will be reducing the delta V and update the voltage. Again, Vn equal to Vn plus 1 and Pn equal to Pn plus 1. Again, you calculate the power. Therefore, if the operating point is here, you will be increasing the voltage and reaching to the maximum power point. If the operating point is here, that is, if the power, instantaneous power calculated is less than the previous one, that means that it is in this region, then reduce the voltage and reach to the operating point. Therefore, return the step 2 and repeat the perturbation and observe the steps until the maximum power point is reached. Another concept is that if delta P by delta V, basically here this operating point is maximum power point, operating point is this one. And to the left side, we can see that one delta P by delta V equal to more than 0, or the slope is more positive. Here the slope is positive. The change in power divided by the change in voltage is more than 0 or positive in this region. Now, if in that case, you have to move the operating point towards, or you have to increase the voltage and bring the operating point towards the maximum power point. Now, if delta P by delta V is less than 0, if it is negative, then you have to reduce the voltage and bring the operating point towards maximum power point. Therefore, basically you are watching what is the slope delta P by delta V. If it is positive, move the voltage, increase the voltage, bring to the operating point. And if delta P delta V is negative, and reduce the voltage, bring the operating point to the maximum. Then once it is reaches to the maximum power point, delta P by delta V equal to 0. Therefore, that is the PV characteristics, and this is the maximum power point. Now let us see the flow chart of Piano algorithm. First, measure the values of voltages. In panel voltages are measured, and will be product of that one will be Vn and Ia. Product of that one will give the power, and we'll be comparing the present power with the previous power. If the both are equal, or the difference of that one is equal to 0, meaning that has been reached to the maximum power. Therefore, that's the maximum power point as such. Now, if there's a difference in the power, that is, if the power calculated is it is more than the previous power, that is in this region. In this region, if it is that one, if power calculated present value is more than the previous power calculated, if it is that condition, then we'll be see that what is the change in voltage also. Therefore, delta P is positive, then we'll see that delta V. If delta V, change in voltage is positive, delta P is positive, as well as delta V is positive, but it is operating in this one, then we'll be reducing the duty ratio and bring the point towards maximum power point. Now, if the delta P is positive and delta V is negative, that is, then we'll be increasing the duty ratio. will be increasing the duty ratio. And if the present power is less than the previous power, in that case delta P is negative. Then if delta P is negative as well as delta V is negative, that is in both cases, then again we will be reducing the duty ratio and bring the operating point to the maximum power point. Therefore, this is the flowchart corresponding to the P&O algorithm, in which we'll be identifying, basically we'll be identifying the delta P as well as delta V polarity. If delta P and delta V polarities are in this case, you'll be bringing the voltage to this by changing the duty ratio. And if delta P by delta V is of course in the negative, then we'll be reducing the voltage by changing the duty ratio and bring the operating point to the maximum power point. Therefore, we'll be watching what is the change in power delta P as well as change in voltage polarities and decide whether duty ratio is to be increased or decreased. And finally, it will be reaching to the operating point will be reaching to the maximum power point. That is, in the maximum power point, delta P by delta V equals 0. Here, delta P by delta V, change in power, power divided by change in voltage, that is positive. Here, delta P by delta V is negative. Therefore, we have to locate the maximum power point, bringing the operating point to the maximum power point by this method. That's P&O, perturbance and observer algorithm, P&O algorithm. Finally, that will go settle at the maximum power point.